request the student to be on time and okay. So let me just start. This is
Sir,
lecture. Yes.
sir, regarding that link which you shared, you are telling to join that your group. But sir, with that link, I just only found that group, sir, that course 2022 Spring PHN 008 Electromagnetic Theory. So, but I could not find that group.
Okay. So yes. You are from which group? I mean, which batch? I would say PPT4 or which
Q
batch you are?
Q7.
Q7. So in the case of Q7, you have this batch representative. What is her name? Let me see. Q7. Okay.
Shivansh.
So Shivanshi Arora. Just contact her because I think she has registered. Just ask her and she will help you.
Okay, sir.
Okay, it is very easy. Yeah. So let me just once again let me look at how many students are there in the class before we start. Okay, still the participation is quite less. I think all of you can see here. Okay, it's fine. It's first couple of lecture. So yeah, effectively this is first lecture. So we are going to start with something that all of us kind of already know, and I also assume that you know about all this stuff. So it is about vector algebra, scalar, and vector. So let me just start by writing what is a scalar. So all of you know about scalar, that a scalar is a quantity that has only magnitude. Fine. So can some of you give the example of some scalar quantities? All of this you know from your class 12.
Work, energy.
Speed. Exactly. Yeah. So
Time.
work, speed. Yeah. Very good. So work, speed, time, mass, distance, temperature. So all of these are scalar quantity. They do not have any direction. They only have magnitude, right? So for example, like time, mass, distance, right? Temperature. Some of you said work, right? So these are all scalar quantity. Now, what is a vector quantity? Vector quantity has both magnitude and direction. Okay, so can somebody of you like say what are the examples? Hmm?
Force,
Yeah,
velocity.
force, exactly. Force, velocity,
Displacement.
displacement, yeah. Velocity, displacement, force, etc. Huh? So let me just write down etc. Now, scalar and vector, these are very well known from our school days. Now, they are concept of field also. Okay, so let me just define along with these scalars and vector. Let me define what is a field. Okay, so field is this kind of physical quantity which is present everywhere in space. So let me just write the definition and then we will elaborate on this. A field is, it can be any physical quantity, right? Like I mean, like we have time, velocity, displacement, distance, etc. Similarly, there is something called field, and it is any physical quantity which takes on different values at different point in space. Okay, so so a field, it is a quantity that takes different values or same value, it doesn't matter, but the thing is like it is present in this space. So can some of you, just based on the definition, can some of you name a few examples of the field?
Sir, magnetic field.
Magnetic field, yeah, of course, yeah, very good. Magnetic field,
Gravitational
electric
field.
field, yes,
Sir,
yes. Electric
As
field you have heard.
intensity is a light intensity.
sir,
Hmm?
can be a field.
Sorry.
Can
Intensity of radiation.
Hmm. I can't hear you properly, but the thing is, okay, two name I heard. One is, so two examples I heard. One is electric field, another is magnetic field. So all of I have already heard. So
The
it is
intensity
correct.
of
In
radiation.
intensity of radiation, okay, yes, yeah, that is also a field because yeah, intensity, yeah. So intensity, yeah. So of course it can be present in the space. Yeah. So that is also correct. Let me yeah.
gravitational field.
Gravitational field, yes, very good. Yeah, so all of these are field. Okay, so by definition, let me emphasize again, let me repeat again, it is a physical quantity that has that kind of fills the entire space. So it has different value at different point in space. Very important concept. Okay, and this will be useful very frequently in this course. So let me just give you one example. What's about temperature T? Okay, so let me just elaborate more on this. Say I have a box. Okay, let's say it is a three-dimensional box. Oops, what kind of box is? Let me just make it. So I have
So,
yes.
so why a field is so why it's written like that a field takes different values to different point in space. Like it can be constant also now.
Hi, it can be constant also. Yeah. So when, like for example, let's say in equilibrium. So this is more generic definition I am saying. For example, yeah, so let's say here I am going to talk about temperature as a field. Okay, because temperature can be, it depends upon the coordinate x, y, z, and of course it is also a function of time. Okay, this is also, we have to remember that it is function of coordinate and time. So generic definition I am saying, well, it has different value at different point, but of course if you are in equilibrium, then the values are same. Right, for example, temperature, if you wait enough, then the temperature will, it will go into the equilibrium. In that case it will have the same value. So it's general definition. So you are correct, yeah, it can have the same value. Fine. So for example, temperature, which is a function of x, y, z, and also it can be function of t. Okay, now let me ask you, before I elaborate more on temperature, uh, this is a field, but it is a vector field or it is a scalar field?
It's a scalar field.
This is a scalar field, correct, because temperature is a scalar quantity. Therefore, the field which is associated with temperature, that is also a scalar field. So this is the example of a scalar field. Let me just write this down before we do something else. So temp, P-E-R-A-T-U-R-E, temperature field. Let me just write it down. And this is a scalar field. So yeah, so suppose I have a block here. So this is a block. Let's say solid block, and suppose I heat it at some place. Okay, so let's say I heat it here. Okay, and what will happen? Actually, this heat will kind of by the conduction, all the block, I mean whole block will get heated, and let's say that this is the
Excuse me, sir.
coolest part. Yes.
Excuse Sir, a lot of students are unable to join this meeting. They've joined another meeting. There are nearly 12 to 13 students in that meeting, and they are unable to join this meeting, so they are not in the class.
Okay, okay. And what is the reason for that? Why they are in other meeting? I mean, they don't know that other class is going on. Why?
No,
Uh,
no, sir. Someone has
So they are
started
just
another
clicking
meeting.
on the join button on the Teams, and they are mm,
directed to a different meeting
Mm-hmm. Okay. So
where only
yeah.
6 7 students are present and they are
Mm-hmm.
not able to join. Even I have shared the link of this meeting, but by that also they are not able to join this meeting.
Oh, why? Okay, just a second.
I don't know, sir. The technical glitch or something.
Okay. Uh, okay, there are 61 students only which are present. 58 are not present. Uh, so, and what happens to the link that I have shared when I schedule the class? Even that is not working, is it? Oops. Then what should I do? S- Um, this is problematic.
Sir, they have to simply leave that meeting and join here.
Yes, exactly. Join again. So yeah, so just do one thing. Just ask them to leave the meeting, okay, and then join again. Okay, just
Sir,
convey
but
this.
but they have to like first leave. All of them have to leave that meeting. Then that meeting will end. Then only this meeting will be showing up.
Oh, I see. So let us. But then the problem is, I mean, whoever is here, other student, then they should not run away. So make sure that all of you are here. So I'm going to leave the meeting. All of you have to leave the meeting, and then let us start again. Huh? Don't run away. Huh?
No, no, sir. We don't have to leave. They have to leave.
They have to leave.
Yes, sir.
The
They have to
ones,
end
the
that
ones,
meeting when which
the
six
ones who
seven
are.
students are present.
Yeah.
Yes, sir.
Okay. Fine. Okay. Fine. So just request them to leave their respective meeting and then join again. Okay. Let us wait for a couple of minutes more because the concept that we are studying this is very important. So just send a message on the WhatsApp that guys please leave the meeting. Whoever is not able to attend, please leave the meeting and then join again. Okay. So I'm going to wait for let's say another couple of minutes before we start the discussion. Fine. Is that okay?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, yeah, because we have just started the course, so uh, I prefer that no one should left behind.
Sir, tell that can you share that screen so that we can write.
Which screen I should share?
So that you were writing with notes, no? That notes screen.
So the things you were teaching about the diagrams and the field and temperature and everything.
So of course the PDF file will be
No,
available,
no,
and
sir.
I
You
will.
can share it on
No,
the
sir,
screen right
if we
now,
are
and so
waiting,
that
so
we can
we'll
make it forward.
complete it till they'll join. So
Okay, so you want me to share the screen?
Yes, sir.
Okay, I think all of you can see the screen now.
Yes, sir.
Okay, so here is the screen. Is this what you want?
Yes, sir.
yes, sir.
That's it.
Okay.
Sir, when the class will be switched to offline, then also we will get notes.
Yeah, because this PDF file I share all the time. So for example, let me, like, you can see the screen, right? So let me just show you. uh for example, okay, this is live. So how do I see? Okay, I don't think I can do here. Can I? Let me see. So I don't think I can show here. But I send you the steps now how you can access the PDF file that I share on the WhatsApp.
Yes, sir. We have that Teams from Teams. We can.
Yes, yeah, yeah. So yeah, so again I will say, like, whoever is able to access these files, just tell the others, because some of the students are doing this first time, and like it is in online mode, so all of us are not very familiar with the software. So yeah, so just help other students also. So let me see. Okay, so what should I do? Should we start again? Okay, because the notes will anyway that will be available. It's already 20 minutes into the lecture. Mhm. Okay, so I'm going to start now because anyway this is available. The notes will be available, and in the next lecture also we can discuss a little bit about this. Okay, so we were here about the concept of field, and I said that a field is any physical quantity that's take on different values, different point in space. And one example I was discussing about the temperature field, which is a scalar field. So I said, well, suppose I have a solid block, and we start heating it from let's say one end, and this other end, which is the coolest one. So here, if you look at every point in this block, that will have different temperature. Okay, and okay, oops. Yeah. So therefore, this is an example of a scalar field. Now, what's about the flow of heat in this box?
So why is it a scalar field?
Why it is a scalar field? Yeah, because if you take any point here, okay, in this block, any point here, it will have a temperature, right? That temperature does not have a direction. Okay, you say 5 degrees Celsius
Okay,
or
sir.
10 degrees Celsius, right? That 10 degrees Celsius does not have a direction, therefore it is scalar. And because it is present throughout the space, throughout the block, therefore it is a field. Fine. Okay, now let us look at this example. Okay, this is something that you already know. Suppose I have a rotating object. So let's say I have a disk. Okay, and this disk is rotating, right? Now there are atoms, many atoms, which are present here. Okay, and suppose this disk is rotating like this. So if I ask you velocity of atoms in this disk, okay, what kind of field is that?
Vector field.
Vector field. Okay, so let me just write it down. Yeah, velocity of atoms in rotating object. Okay, so this is the example of a vector field. Because if you take a, if you look at any atom, right? So this one is having a velocity, and velocity is a vector quantity, and throughout the disk, this velocity is present everywhere in space. Now let me ask you, what's about for uh, flowing liquid? Okay, so suppose you have a tube, and in this tube some liquid is flowing. Okay, so this is also example of a vector field. Okay, so this is also a vector field. Okay, because your v, the velocity that is there, it is of course it is a function of x, y, z. Okay, so and of course the velocity also depends upon time, depending upon whether you are in equilibrium or not. But the thing is, this is a vector field, so velocity is a vector field. Now let us look at some other example that you said. Of course, the electric field you said. and some of you also said about magnetic field. Okay, so they are all vector field. Now,
So,
yes,
sir, current is a scalar quantity, no?
current.
Yes, sir.
Yeah, yeah, current is look, because okay, what is current? First of all, let us see what is current. Current is the flow of electrons. Okay, it is the flow of electrons. So current is a flow of electron. So when we discuss current, do we talk about direction or not?
Yes, sir. We talk about it in magnet.
Yes, sir.
We talk about direction. So if we talk about direction, then I will put it in the vector field. And if we don't talk about direction, then it is not a vector field. And moreover, so yeah, so before we go to current, so it's like, yeah, and current is of course present everywhere, is it? So suppose I have a wire here. Hmm? So current is present everywhere. Does it has direction?
No, sir.
No, sir, we do not talk about direction in current. We
Yes, sir.
usually are like ask question like from which node to which node the current flows, but we never
Hmm.
like specify like it's flowing in the north or south, sir.
Yeah, and also like I have not heard the term, current field. Okay, so I have not heard whether current is a field or not. Okay,
Sir, I was
so
asking about electric field because this field is electric current only, no?
yeah, yeah, electric field is of course a field. So when we talk about electric field, we say, well, suppose you have a charge here. Okay, you have just a charge here, Q. Because of this charge, okay, there's a field everywhere in space. Okay, so I can define what is the field here, what is the field here.
Yes, sir, got it. Sir, I
Yeah,
misunderstood it.
yeah, yeah. So it is present. So if we go back to the definition, we can say, well, it is some quantity which has different value, and it fills the entire space. Okay, so it is present everywhere, right? This field is present everywhere. So therefore, electric field and the same concept is there for magnet. So there is magnetic field. Now let us look at some basic operation. Okay, on vectors. So all of this, for example, addition. We know that for a vector, okay, addition is commutative, and if we multiply it by a scalar, okay, so suppose I have a scalar a and I multiplied two vectors a plus b. In that case, I have a plus ab. That means that multiplication by a scalar is distributive. Okay, so all this now let us look at the dot product of two vectors. What is a dot b?
The modulus of A into modulus of B into cos theta, where theta is the
Cos
angle
theta,
between A and
where theta is the angle between them. Now, very good. So yeah, so here a dot b is the product of a times the, so you can call it, well, this is the product of a times the projection of b on a. Okay, or you can also say it is the product of B times the projection of A along B. It's the same. Now another thing that we know about vectors is the cross product of two vector. So what is A cross B? Yes.
That
AB
thing
sin
has
theta.
magnitude.
Yeah, correct. And what is n cap here?
Unit vector along
That
cross.
Yes, it is unit
perpendicular
vector. Yes, which is perpendicular.
to
Sir,
both A
it is
and
a
B.
unit vector perpendicular to both vector A and B.
Yeah, to the plane of A and B. Correct. Okay. Now, okay, this is something that I need later. So here everything is pretty obvious. But let me ask, what is A cross A?
0.
Zero.
This is zero. So I need this after 3-4 lectures, huh? That A cross A is zero. Okay. Now, suppose you have to determine what is A cross B, then you also know you can write X cap, Y cap, Z cap, and the component of A, AX, AY, AZ, BX, BY, BZ. So this is how you can determine A cross B. And for the direction, okay, you have the right-handed screw rule. So all of this you know. Now let us discuss very quickly about the triple product. By the way, can you read my handwriting? It's fine, huh?
Yes, sir. Very good. Right.
Yes, sir.
Very good. Very good.
Okay. So now let us look at scalar. Yeah. Now let us look at scalar triple product. So it is A dot B cross C. Okay. So earlier we have two vectors. Now there are three vectors. So by multiplying three vectors, we can either have a scalar quantity or we can have vector quantity. So the first thing is scalar triple product. And how do we calculate this? Just by the this matrix ax ay az, bx by bz, cx cy cz. Now yeah, so okay, let me just ask this: what is a dot a cross b?
0.
It is zero. And
Zero.
what is the reason, and what is the reasoning that you will give that it is zero?
Sir,
Is
because A
log.
is perpendicular to that A cross B.
Perfect. Perfect. Okay, so what he said is that A cross B will be perpendicular to both A and B, and so if you take the dot product with A again, then it will be 90 degree. Therefore, the dot product will be zero. Okay, and you can also check this just by putting the component of this into the matrix, so that will be zero. Okay, so now you also know that A dot B cross C is nothing but the volume of parallelepiped, right? So it is the, this is the volume of the pipette, and it is generated by, let's say, A, B, and C here. Now, what's about, okay, let me just write here itself. What's about the vector triple product?
Sir, I
So,
have,
yes,
sir, if the scalar triple product is volume, so then if we invert the coordinates, where A becomes minus A, B becomes minus B. So then the volume will become negative, but actually it should be positive, right?
Yeah, volume has to be positive. Yes.
But it comes out to be negative when we invert the coordinates.
Uh,
It's
mhm.
actually because we actually changed the orientation of the volume for measuring it, like a dot b cross c. We did
But
a
volume,
b dot c. This means we are actually reversing the plane, the normal vector of the plane.
Yeah, actually, it's, I mean, what is happening here? Oh, oops. Let us say I have vector A like this, vector B like this, right? And so this is A, this is B, right? So A cross B this, right? And then, so sorry, this is B cross C. Okay, let me just write it down as, so let's say this is B, this is C, so this becomes B cross C. Now A is, let's say, here, okay? So when we take the product, it becomes the volume. Now you are saying, well, what happens if I take instead of A, if you take A here, right? This is your question, right? Earlier it is plus A, if you make it minus A.
yes,
Is it
and B
correct?
also
Yeah.
becomes minus B, and
Yeah,
C
so
also
this,
becomes minus.
yeah, so
So
it's like, yeah, so it doesn't matter, right? I mean, in that case, you have volume here. And all of these are physical quantity, right? It doesn't matter that volume in that direction or volume in that direction. So you get, let's say, minus something, then what you will say, well, I have to take the mode of that. Okay, because
so
negative
may I,
volume.
so
Yeah,
may I
because,
explain?
yeah, sure, sure, sure.
Sir, A cross B contains mod A and mod B and the angle between the two vectors. So if we even reverse it, then the angle will also be the accurate angle between them, no?
Yeah.
And when we
And the
take the
same
dot
thing, yeah.
product, the
Yeah,
same.
and the same, yeah, and the same thing is later true for when you take the dot product, A dot. Because when you come here, in that case also you have mod of A. Okay, fine.
Yes, sir.
Yeah. So this is what happens. I mean, and if you look at pictorially, then I mean, you have vector A here. So in that case, volume like this, because volume is anyway, it is, in that sense, it is origin independent. It doesn't matter where you put your origin. Volume is volume. Okay. So let me just, you got it now. Okay. So now let us look at vector triple product. Vector triple product is defined like this. So what is the formula for this?
A dot c b vector minus
C B vector minus A dot B into C vector. Okay. So this is also a formula. Let me just put it in a bracket. Now let us look here how vector transforms. And what do I mean by that?
So can you please show the previous page for us again?
Yes. Okay.
So just one second. Yes, sir.
Okay. So now let us see how vector transform. And what do I mean by that? Let's suppose I have a vector A. Okay. And let's say this is my x-axis. This is my y-axis. And the question I'm asking, if I rotate this x and y axis by, let's say, theta degree. Okay. So now my new axes are this is x prime and this is y prime. And I have rotated this old x and y by theta degree. Oops. So this is x, this is y, this is x prime, and that is y prime. And I have rotated the axis by theta degree. So this is my theta. Okay. So let us do a little bit of trigonometry here. So if I rotate it, and let's say initially this vector A, it was making an angle phi with the x-axis. So I have a vector A, it was making an angle phi with the x and y, and I rotate my axis by theta degree. And the question is, what will be its coordinate? Okay, so this is the question that we are going to look into. So let me just write here, what is ax prime? So ax prime will be, okay, I have to be parallel. Again, I think I'm drawing wrongly. Oops. Fine. So what will be the ax prime? Ax prime will be a cos phi minus theta. This is my ax prime. Okay, this length is the ax prime. And this will be ay prime. Okay, so let us expand this. This is a cos phi cos theta plus sin phi sin theta, and cos theta and sin theta. Okay, so a cos theta will be ax. Therefore, I can write that ax prime, okay, will be ax cos theta plus ay sin theta. Equation number one. Okay, and what will be the value of ay prime? That will be a sin phi minus theta. Okay, I can expand this. That will be a sin phi cos theta minus cos phi sin theta. And again, these values I can put because I know what is ax and ay. So therefore, that will be ay cos theta minus ax sin theta. Okay, so this phi I has eliminated. Now, in the matrix form, or in the matrix notation, let's say, I can write that my component of that vector in this new transformation, they will be sin theta cos theta minus sin theta cos theta and ax ay. Okay, and I think this is something that you should remember also. So let us put it in a box. So what we have done here, we said, well, let's say I have a vector a. Okay, and I have coordinate axis ax and x and y, and I rotate the coordinate axis. How the component of a will transform? So in this new rotated coordinate axis, I have the component along the x direction is ax prime, and along the y direction it is ay prime. Then what is the relation between this rotated frame and the initial frame? Fine. So this part you understand? I'm still, going very slow here. Any question about this? Hmm?
Sir, can you show the three-dimensional version of this?
Okay, in three dimension, in three dimension, then what you have to do is, first of all, you have to fix the axis about which axis you are rotating. Okay, so if you rotate, for example, about z axis, then the third coordinate will be 0, 0, 1 in that case. Okay,
Sir,
so of course you can,
other than
yeah,
Z. other than XYZ.
Yeah.
So
No,
then
no,
what?
XY will be, yeah. So it will be like, I don't remember exactly, but I think it will be 0, 0, 1. So it depends. Like if you are rotating about Z axis, so that Z axis will not transform, right? I mean, around that it will not transform. So your AZ prime has to be equal to AZ. Okay. So therefore, in the matrix, it will be 0, 0, 1. Okay. So of course, I can do it later. I mean, right now I don't have exact a transformation equation with me, but of course we can extend it to 3 dimension. Okay. So all this is in 2D. Fine. So if you are rotating about x-axis, okay, in that case, uh, the transformation about x-axis will be fixed. So in that case, you will have ax prime equal to ax. If you rotate about z-axis, then az prime will be equal to az. Therefore, in the matrix, somewhere it has to come 0, 0, 1 has to come. Okay, now let me ask you a very simple question. It may be a stupid question also. So let me just ask you, suppose uh, there are nx pears, ny apples, and nz oranges. And the question is, oops, is n equal to nx, let's say x cap, plus ny y cap, plus nz z cap, is a vector? Anyone?
Yes, sir, it's a vector.
It is
Sir, it is
vector.
not. Sir, it is not a vector because it cannot be transformed.
Yes. Anyone else? It is a right
Sir,
answer. Anyone else?
but sir, nx, ny, and z are definitely numbers, and you have written n equals to a number, scalar times x vector plus scalar times y vector and scalar times z vector, so it's a vector.
So what is x cap here? You know, x cap is a some kind of, you can say a unit vector. So this is a unit pears or something like this. Ny is a unit apple, and nz is a unit orange. Anyone else?
Sir,
Is this a vector or a
sir,
scalar?
if
That's
the
right.
XYZ cap defines the spatial vectors like unit vectors, then it is a vector. And if they define something else like unit pears, unit apples, or unit oranges, then it is not a vector.
Anyone else? Okay, so let me just write down the answer. It is not a vector. Okay, so when we say nx is the number of pairs, and let's say x cap is some kind of, unit vector, unit pair or something like this. The thing is, this is not a unit. This is not a vector, and the reason is discussed right here. Okay, because we have to look how a vector transform. In this case, it doesn't matter, how you transform your like how you rotate your axis. Your peers are not going to become apples or oranges. Okay, you got this point? It doesn't matter. I mean, you can take whatever axis and then you rotate that axis. Peers are not going to transform into apples. Therefore, this is not a vector. So let me write down the right reasoning for this. So the reason is, mm, axis. Also, you can look for your mechanics book, like Mariam and Crick. So you can find this in
Sir, which mechanics?
dynamics part, because there you have talk about, like there we have talk about moment of inertia, tensor, and so on and so forth. So there you calculate, this moment of inertia about any arbitrary axis. So first you calculate about x axis, y axis, z axis, and then we talk about moment of inertia about any arbitrary axis. So I think here also you can find. So just look for this book, Engineering Mechanics and Dynamics part. And the authors are Mariam and Craig.